Welcome back, class. Just to reiterate from the previous section, last week we learned a lot about how to graph the equations of the line and how to manipulate equations of a line. We learned about the properties of an equation of a line, such as the slope and the intercept of a line. And so, as it turns out, one of the interesting features whenever you're dealing with a problem that requires you to graph an equation of a line is that while it's true, we can always create a table of points. We select, say, a few x points and then find the corresponding y value by performing a series of calculations. While this is in fact true and it will always work, in order to say graph an equation of a line. In this instance, we have an equation of a line y is equal to 2x plus 5. And if we had given ourselves a table of points, maybe -1, 0, and 1, we could have found the corresponding y points. Well, 2 times -1 is -2, so you have -2 plus 5, or 3. 2 times 0 is 0. 0 plus 5 gives you 5. 2 times 1 is 2, plus 5 gives you 7. And so you would have been able to find that you have 3 points along this line. In this instance, one at -1, 3, should be right there, one at 0, 5, and one at 1, 7. So something that looks kind of like this, okay? And your graph, of course, doesn't have to be perfect. Now, while this is, in fact, true, and if you do all of this work on your own within the homework, that's great. It turns out that graphing the line can often be simpler than this because we can exploit a couple of the properties of the line itself. For example, whenever you have an equation, the number that's floating out in front is what we always call the slope intercept, or the intercept, the y-intercept in particular, of a line. One of the interesting features of the y-intercept is that it allows us to then plot the line a lot more quickly, because instead of sitting here and creating a table, I'll know that one of the features of the equations of this line is that, geometrically speaking, this line will always cross the y-axis at its y-intercept. So I'll have a point along the line exactly at +5, so the 0.05 to be specific. And this line will cross exactly at this point in some way, shape, or form. Now, of course, we have to determine the slantiness of the line. Is the line going to go like this? Is it going to go like this? Is it going to go something like this? And in order to determine the slantiness of the line, we naturally only have to look at the slope of the line. Remember, we said the slope is the slantiness of a line. And so when you have a situation where the slope is 2, we can say that's the same thing as having a slope with a rise of 2 and a run of 1, which is to say that you can go up on your y-axis or up vertically from whatever your point for the intercept, the y-intercept in particular, happened to be. In this instance, we had a point at 0, 5, and so we can go up 2 units vertically from 0, 5, and then over horizontally 1 unit, and we can place a point and simply draw a line. Okay, that's all we have to do if we want to graph an equation of a line. Of course, another alternative to this, which takes a little bit more time, is to isolate your y-intercept as well as your x-intercept. Recall that an x-intercept occurs where y equals 0. So the x-axis itself exists everywhere that y happens to be 0, or said another way, on the ground. Okay, if we think of this, the horizon, this horizontal line, as being the ground. We just have an imagination where we're saying this horizontal is like the ground to us. then if you don't go up from the ground, you have no height for your line, you're just on the ground. And so your x-intercept is going to always occur where y is 0. So another way of, say, determining the equation of the line would be to, of course, find out what your y-intercept value happens to be, which is very easy to do when you've got an equation of the line in the form of y is equal to mxb to begin with, which is exactly what we're dealing with here. But then an alternative strategy would be to set y equal to 0. And now you have a two-step LA of E, because when y is 0, we simply need to solve for our x value. We would, of course, add a -5 to both sides of our equation, and we'd have -5 plus 0, or -5, is equal to 2x plus 0. 2x plus 0 is just 2x. And we can multiply by 1/2 on both sides of our equal sign, and you get x is equal to -5/2. So -5 halves should be what? A -2.5 somewhere. So we'll go 1, 2, and there's 3. So if I go to something like this, you'd actually have a slope that's a little bit, and maybe I didn't put my notches exactly straight. So my line isn't looking too good here, but nevertheless, you could connect the dots between your y and your x intercept. And I hope that makes sense, because in this particular chapter, what we're going to learn today is going to require us to be drawing, or be capable of drawing, a lot of different lines. Okay, so if we can master that skill, really focus on mastering the skill of drawing lines. I know that the course progresses rather quickly, but that's one of those skills that is extremely important for us to learn. So what we're learning today in section 3.5 is called the point slope equation. Last week, we learned that there were a number of different ways that we could represent the equation of a line. One such method we called the general equation of a line, which has this odd form ax plus by is equal to c. And we may not necessarily at this point in time understand why it might be necessary for us to represent this x and y relationship as being maybe an additive relationship with one another equal to some constant. It may not necessarily make a whole lot of sense to us, and that's okay. But nevertheless, this general equation of a line is one form which we can find lines in. And then another form, of course, is what we call the y-intercept formula, which is our ordinary y equals mx plus b equation, or the ordinary equation of a line, as I like to call it, where m is your slope, b is your y-intercept value. And of course, the y-intercept formula, at least initially, appears to be much more important in terms of its impactfulness, because it immediately allows you to isolate your y-intercept if you so desire to know that information. Of course, you have the slope of the line, and so you have all of the information that you need about the line right at your fingertips just by looking at the y-intercept formula. But it turns out that there is yet another formula of a line that's called the point slope equation. And what the point slope equation allows us to do is it allows us to solve a number of rather tricky word problems that deal with the properties of a line. So let's dive right in. If you recall, the slope equation is of the form m is equal to y2 minus y1 all over x2 minus x1. And what this equation essentially represents formulaically is it represents the relationship between any two points along the line. And it turns out that the slope is simply the ratio of the height or the change of the height, to the width, the change of the width or the change of the horizontal displacement, if you'd rather, as we go along the line. Okay. And so if you have some sort of a y2, y1 and an x2, x1, you can always divide these quantities by each other in order to obtain the slope. And so consider, however, a problem statement. Find the equation of a line whose slope is 2, which passes through the point, and let's give ourselves a nice point, 0, 1. That's a pretty nice point, if you ask me. Okay, so it says find the equation of a line whose slope is 2, which passes through the point 1. So our problem solving strategy for word problems always starts out with us trying to identify the important information, as we've learned over the past 2 or 3 weeks now. And what that looks like is we are going to identify our known information. We are going to identify our unknown information. So we are given 1 point. We're given the point 0, 1. Of course, we also know that we have a slope to work with, that we can work with, which is that our slope is 2. In terms of our unknowns, we don't have an equation of a line. Y is equal to something. Now, the problem statement itself also asks us to find the equation of the line, so we certainly wouldn't know what the equation of the line happens to be, because that's exactly the problem statement. However, we do have some equations that are pertinent to this type of problem statement. You might already be writing down y equals mx plus b, okay? Because this is, in fact, one of the equations of a line. Now, secondary to this, you've got ax plus by is equal to c. These are 2 equations of a line. However, if we were to select from the y-intercept equation, this first equation, what we need in terms of the information from the problem statement is we need a slope. So you have to know what the slope is. But then the second thing is we need the y-intercept. We do, in this instance, have the slope, but you'll note that what is conspicuously absent from the problem statement is the y-intercept information. So we don't know what the y-intercept happens to be. Most notably, it doesn't appear to be obvious how we would find out what the y-intercept was, because we're not even given any sort of remote information pertaining to that problem statement. So you might be able to construct a partial equation, y is equal to 2x plus b, but what is the b value? So, it's just not going to be possible. Now, for equation 2, the general equation of the line, you need to know what your a, b, and c coefficients happen to be. So if you know what the a, b, and c coefficients are, then you can definitely use the general equation of the line, but unfortunately that's not the case here, so we can't do that. The only other equation that we might be, kind of grasping at would be this slope equation, where we've got this y2 minus y1 over x2 minus x1, right? But usually the slope equation allows us to calculate the slope. And so in this instance, the issue here is that we already have the slope. So the use case would be if we needed to find the slope. And since that isn't the case, this formula, at least it's not necessarily obvious that we would use this particular formula. So there again, we're defeated. And at this point in time, students are probably sitting back and scratching their heads and saying, man, this is a little bit of a brain teaser. What are we going to do here? And this is exactly the kind of problem statement where we're going to need to introduce what is known as the point slope equation. It turns out that whenever you have the equation of a slope, you can actually perform a little bit of a trick, because remember, for composite fractions, you always have a fraction as being defined as any number divided by some other number, which is to say that you can always take a number and multiply it by 1 over whatever your other value happens to be, in this instance, b. So a over b is the same thing as a times 1 over b. And we can kind of use this trick right here. We can say that y2 minus y1 is the same thing as y2 minus y1 times 1 over x2 minus x1. Now here's the deal, students. Recall our linear equations of one variable. Suppose that you have c is equal to a times 1 over b, and you wanted to solve for a. Well, with our LEOV equations, what we know is that our basic tool set that we have available is either to use the multiplicative inverse or the additive inverse, unless there exist exponents in a problem statement, and then we have another story entirely. However, in this particular instance, we're not dealing with any exponents, and so it seems to be the case that we should be able to use a multiplicative inverse. And what are we going to use as a multiplicative inverse? Well, we look to the term that we would like to remove. If we're solving for a, and we have a being multiplied by this 1 over b term, well, the 1 over b term is kind of useless to us. We don't want the 1 over b term. We want to remove the 1 over b term. And so that's exactly what we're going to do. We're going to multiply both sides by b over 1. And so b over 1 times 1 over b, this is going to just be b over b. And b divided by 1 is just b. So now you've got b divided by b, or just 1, is equal to c times b. And anything times 1 is just that something. So we've not violated any rules of algebra by simply multiplying on both sides by some value. And we certainly didn't violate the rules of algebra by saying b divided by b is equal to 1. Okay, because that's the inverse law. And so what we're going to do is simply a fancier version of this trick to isolate our a. But in this instance, you can kind of think about your a as being this y2 minus y1, and your b being x2 minus x1. Because while it's not necessarily immediately obvious to students that your a would in fact be y2 minus y1, if you did know what your y2 was, or your y1 happened to be, you could indeed calculate your a by subtracting y1 from y2. And similarly, for the same exact reasons, even though x2 minus x1 seems to be this process where we've got two different values, one being subtracted from the other, if we knew what x1 was, if we knew what x2 was, we could take x1 subtracted from x2, and boom, we'd have our b value. And so here's where the mental gymnastics comes into play. We are going to multiply both sides by the inverse of this 1 over x2 minus x1 value, or said another way, the 1 over b term. And how did we do that down here? Down here, we multiplied by b over 1. So what we need to do is we need to multiply both sides of this equation. It's going to look kind of funny, but it's mathematically correct, by x2 minus x1 all over 1. And so now you've got this y2 minus y1 multiplied by 1 over x2 minus x1. And that's being multiplied with x2 minus x1 all over 1. And these terms right here, I don't even necessarily need to do any more mental math. I know that this will cancel out and become 1 because I've done nothing illegal. I've simply used the inverse law. And so now I've got 1 times y2 minus y1 is equal to m times x2 minus x1. All right, well, 1 times y2 minus y1 is simply y2 minus y1. And we've got x2 minus x1. Everything's great, and you are finished. This is going to be your new formula. And note, all I did was I switched the sides where I'm writing my y2 and y1 equation. So I just did a little switcheroo, which is totally legitimate. So you can do a switcheroo in mathematics. Okay, this is called our point slope equation. So the point slope equation is always written as y2 minus y1 is equal to m times x2 minus x1. And what this equation allows us to do is it allows us to find the equation of a line. So its use is that it allows us to find an equation of a line if we are given an m and a x1, y1 coordinate pair, meaning we need at least 1 point and a slope. And if we have 1 point and a slope, we can always plug in our values into this particular equation and we are good. So you're going to write out your y2 minus y1 is equal to m times x2 minus x1. And going back to this previous problem statement where we know the slope is 2 and your point is 0, 1. So our point that we're given is 0, 1. Our slope is 2. Note that for any point of a line, you always have an x, y coordinate pair. But in this instance, in order to solve these types of problems, what is most likely best for students to do is to go ahead and label your first value of the coordinate pair, your x1, and then to label your second value of the coordinate pair, your y2. I'm sorry, your y1 rather. Now, while you could label the coordinate pair x2 and y2, because why not? Points along a line are the same thing. It is customary. It's customary for solving these problems to plug in for your point, your first value being your x1 and your second value of your point being y1. As long as the subscript of these points are the same, it does not matter whether you pick y1 x1 or y2 x2 for your point. It will give you the same answer. It's just that one is a little bit easier, so that's what I'm going to go with. So I set my x1 to be 0, my y1 to be 1. So now I've got enough information to work with. I'll have y2 minus 1 is equal to 2 times x2 minus 0. And at this point in time, I'm going to do one little change in my formula. I'm going to erase my subscript. We will then multiply by 2. 2 times 0 gives us 0. And I've got y minus 1. So we've got y minus 1 is equal to 2x because 2x minus 0 is just 2x. And I can go ahead and use a multiplicative inverse on both sides to isolate my x. Or actually, I don't want to do that. I wanted my formula in terms of y, rather. So backing up a bit, we've got y minus 1 is equal to 2x. Let's go ahead if we wanted to isolate our y, because that's like how we like writing our equations. We'll have y plus 0 is equal to 2x plus 1. And we've got y is equal to 2x plus 1. And that is our equation of a line. So this is our answer. Either way, really the challenge of these types of problems is twofold. First of all, actually it's threefold. I'll explain. First of all, we have to be able to correctly interpret the problem statement. By that, I mean we need to be able to read the problem. The second thing that we need to do is we need to identify the pertinent information, the important information inside of the problem statement itself. So we need to be able to identify that we have a point that we're working with, we have a slope that we're working with, we need to be able to identify our unknown values, our known values, our equations that are necessary for solving these types of problems. And then the third issue is simply algebra. And by this point, since we've been working with manipulating algebraic expressions for, we're going on 6-7 weeks now, we should be more or less familiar with how to perform these operations. When in doubt, simply go back to using a multiplicative and or additive inverse in order to make sure that you are performing your math correctly. And my recommendation would be to go one step at a time. One step at a time is going to lead you to the most correct answer, or at least an answer that you can double check. All right, so find the equation of a line whose slope is -3/4 and has a point -4, 2. Note that we will plot out our known information. We know that the slope is -3/4. We know that we have a point of -4, 2. If we were to look at equations of a line that are pertinent to this problem statement, you might have a y equals mx plus b, and your unknown values, of course, being that you do not know what your b happens to be. Your x is actually something that really doesn't matter because we can just pull points out of thin air in order to plug in for an x if we did have an equation, right? So x would always be our what is known as our independent variable. And once we just pick points, we're able to find the corresponding y value, our dependent variable, as a consequence of this. So we don't, we take for granted the fact that y and x, of course, are this dependent and independent variables. That's not really something that we have to plot down for our unknowns. Now, if we had looked at y2 minus y1 is equal to m times x2 minus x1 equation, you'll note that we have all of the information that we need in order to solve this problem statement. We've got a slope, we've got a point, we're ready to rock and roll. Let's go ahead and we'll denote somewhere on our page what our x1, y1 values are going to be. And then, of course, you can use your distribution law. Negative negative is a positive. Positive times a -3/4 will be a -3/4 times that value. Of course, 4 times 3 is 12. 12 divided by 4 gives me 3. So I should have a -3. And then -3/4 times x is simply -3/4 x. It's okay to have a negative in front of your x. It's not going to be the end of the world. Now, at this point, we are essentially one step away from solving this problem. We need to go ahead and use that additive inverse on both sides of our equal sign. You're going to get y is equal to -3/4 x minus 1. And that is all you have to do. All right. There are a couple of caveats, and that is you will have to be able to find the equation of a horizontal / vertical line. Note that a horizontal line is just a line that perfectly passes through the y-axis. And it usually is of the form x is equal to, I'm sorry, not x is equal to some value, but y is equal to some value. There we go. So this is my y-axis, this is my x-axis. And at some point, you'll have a line and it crosses straight through the y-axis at the value 0a. By contrast, for vertical equations rather, you're going to have a vertical line that passes straight through your x-axis at some value a0. Okay. Now, what does this look like? Find the equation of a horizontal line which passes through the point, when we'll say the point is 2, 5. Okay, so for this word problem, you read that you are dealing with a horizontal line and you're trying to find the equation of a line that passes through the point 2, 5. So if you were to graph this out, 2, 5 is roughly this point right here. And it says that you have a horizontal line. So it's going to go right across the horizon. It's going to be straight from the left to the right. And it passes through 2, 5. What equation is going to model this situation? Well, the only equation that can do this is going to be y is equal to 5, where the 5 is obtained by looking at the y coordinate pair, the y coordinate just of the coordinate pair for whatever point you happen to be given. Similarly, if you were trying to find the equation of a vertical line which passes through the point 1, 5, you would read that you need to find the equation of a vertical line. That's your key phrase that you're looking for. You're going to draw it out. It says that the line itself passes through 1, 5. So I'm going to go over 1 and up 5. There's the point that I plot. And it says that I'm dealing with a vertical line now. So I'm dealing with a line that goes straight up into the sky. Vertical means straight into the sky, just like that. So we look to our formula that represents the vertical line situation. We see that we will always have an equation x is equal to some value. In this instance, the value is a. And we simply look at the point that we're given. We look to the x coordinate of this point. In this instance, our x coordinate is 1. And so we say that the equation of the line that represents this particular vertical line is the equation x is equal to 1. The long and the short of it is, if you have x equal to some value, you're always dealing with a vertical line. If the value happens to be positive, you're dealing with a line that is to the right of the y-axis. If the value is negative, the line will be to the left of the y-axis. Whereas whenever you have an equation of a horizontal line, you have y equal to some value. And if the value happens to be positive, your line will be above your x-axis. If the value is negative, the line will be below your x-axis. So regardless of what line you might be dealing with, it's rather straightforward to find vertical and or horizontal lines. or equations which represent vertical and or horizontal lines. All right, this brings us to section 3.6, which is over the topic of parallel and perpendicular lines. It turns out, just as a definition, that when you're looking at parallel lines, okay, the way that you draw parallel lines is you're going to draw a line. You put a point on the line and you kind of draw down to a point on your axis, and then you move over some amount to another point on your axis, and you try to essentially line up these points. And there you go. There's your parallel lines. So this is what parallel lines look like. What's interesting about the equations of parallel lines is that for any two equations, y is equal to mx plus b, the parallel lines themselves will have the same angle measurement. So suppose A represents the measurement of the angle of our parallel lines. From Euclid's fifth postulate, if you recall back to your high school geometry course, Euclid's fifth postulate says that the angle of the parallel lines will always be the same. And if it's not, if you have, say, one parallel line that's not the same, does not have the same angle, then what will happen is it won't be parallel because they'll actually meet together at some point if we were to extend the line. So whereas if you do have the angle being equal between the parallel lines and, say, a line that is drawn completely straight through either of the lines that are parallel to one another, then what happens is they will indeed stretch out to infinity, and all of the points will never meet one another. Okay, forever and ever. Now, what's interesting is that Euclid's postulates are equivalent in the language of modern mathematics, modern Cartesian geometry, as saying that for any two lines where maybe you have a y is equal to m1x plus b, and your second equation of the line being m2x plus b, if y1 is parallel to y2, then what that implies is that the slope of your first line is equal to the slope of your second line. The slopes have to be equal in order for lines to be parallel with one another. And the intuition for this is simply that the slope indicates slantiness of your line. So instead of, say, measuring the angle or the spread between, the line and your horizontal axis, you had instead measured the spread of your line as being a ratio of the rise to the run. You would effectively be doing the same thing. And so what it means is that your slopes need to be the same in order for lines to be parallel, because anytime the slope is not parallel, then one of the lines is either rising or running faster than the other line. And what it means is that at some point in time, if you kept extending the line out, they will indeed cross one another. Okay, so you'll often be met with determine whether the equation of a line are parallel. So you might have one line, y1 is equal to 2x plus 5, and another line, y2 is equal to 2x minus 6. Well, since the slope of my first equation is equal to 2, and the slope of my second equation is also equal to 2, i.e. m1 is in fact equal to 2, the slope of your first equation is in fact equal to the slope of your second equation, that means that y is parallel to your second line. The y1 is parallel. The first line is parallel to your second line. Said another way. Usually the problems won't be this nice. They're actually going to ask you to perform some formula rearrangement. So you might have a 3x plus 4y is equal to 7 and a 5x plus 2y is equal to 4. And they'll ask you whether or not the equation is, whether these two equations are parallel lines. Okay. And so if you do get an equation like this or a system like this, where you have two different equations, then what you're going to need to do is you're going to need to perform some variable rearrangement. You're going to need to, in fact, solve for y, i.e. get y by itself on one side for both the top and the bottom equation. So what this looks like is you're going to use that additive inverse to move your x from the left to the right side of your equal sign. Your x values will disappear. You've got 4y is equal to 7 minus 3x on the other side. You're going to need to use that multiplicative inverse now. Multiply your 4y by 1 over 4. And everything on the other side of your equal sign gets multiplied by 1 over 4 as well. Now, you do have to do some cleanup using the distribution law. So I'm going to go to another page. I think I had 7 minus 3x. So doing distribution, we get 1 over 4 times 7 minus 1 over 4 times 3x is equal to y. 7 times 1 gives you 7. 3 times 1 gives you 3. And if you do some rearrangement, you get negative 3/4 x plus 7/4. And this is, in fact, your slope of your first line. Now you have to find the slope of your second line. So you have to repeat this process over again for the slope of your second line. In this instance, you will go ahead and use your additive inverse. You get 5x plus negative 5x, which gives you 0. And 4 minus 5x on the other side. You get 2y is equal to 4 minus 5x. Go ahead, use your multiplicative inverse at this point. You've got to multiply everything on the other side of the equal side, okay, guys? And you're going to get y is equal to 1/2 times 4 minus 5x, or said another way, y is equal to 4 over 2 minus 5x over 2. 4 divided by 2 gives you 2. 5/2 is simply 5/2. So we have y is equal to 2 minus 5/2 x, or said another way, if we use the commutative law, y is equal to negative 5/2 x plus 2. And this is our second equation. So for our second equation, you'll see that our m2 is equal to negative 5/2, whereas for our first equation, our m1 is equal to negative 3/4. And so as a conclusion, since m1 does not equal m2, y1 is not parallel to y2. And that's all we have to write. That's all we have to do. Now, here's the deal, gang. Using the long form additive and multiplicative inverse is, in fact, rather laborious for these problem statements. And so we are going to have to utilize a kind of shortcut as we go through these problem statements. But the shortcut itself has to be well thought out. And it turns out that for linear equations of the form y is equal to mx plus b, or of the general equation of the line, you can indeed perform column-wise subtraction in order to move terms from one side of your equal sign to another. You can also use division on both sides for these particular equations. And the reason for this is that you may represent the left-hand side of any equation as this, L1 is this is just an equation with a linear combination of terms on one side, on the left side, and then that's equal to an equation with a linear combination of terms on the other side. And it turns out that if you were to, say, multiply both of these equations with some value, in this instance, say the value a, then what happens to your linear combination is that the linear combination just kind of is stretched by some amount. And the equation balance, of course, is preserved because multiplication on both sides of an equation in general is legitimate. And it'll especially be legitimate for a linear combination of terms. Here's the deal. For the same reason, we may, of course, go backwards between a linear combination of terms as long as we are careful about dividing on both sides of our equation in order to arrive at our original, equation balance that we might have been working with. And so this is to say, if you have a system for y is equal to 2x plus 5, instead of using the multiplicative inverse, you can, in fact, divide everything on the left-hand side of your equation by 4, as well as everything on the right-hand side of your equation by 4. And then this allows you to more easily, or perhaps more efficiently, be able to obtain your equation or your new equation of a line and perform variable rearrangement. For similar reasons, because we started with this principle that an equation is always balanced by being able to, add some value to both sides of an equal sign, and because we are dealing with linear equations here, or linear combination of terms, where everything is just, all of our terms happen to be linear in this instance, and all of our terms happen to be a combination of addition operations, and or even if there is, in fact, a subtraction operation somewhere in the equation itself, what's going to happen is you may, if you wanted to, turn back the clock and go backwards between a complicated expression, linear combination of terms. You may perform subtraction column-wise on both sides of your equation. Okay, without breaking a general rule of algebra. Now, in general, you can't do this for a variety of different equations because you do have to watch out for what is called the associative law. But for a linear combination of terms, where everything's being added together, regardless of how many terms you might be dealing with, you can indeed kind of shortcut the process of using your additive inverse, because the subtraction process column-wise will indeed allow you to essentially undo addition on both sides with a linear equation. Now, this doesn't work it doesn't work in general, but for linear equations, one can, of course, use this shortcut. So if you had, say, 3y plus 5 is equal to 7x minus 4, you might use the shortcut of subtracting 5 on both sides. And the reason that you can do this shortcut is because you are essentially undoing an addition on both sides setup that you might have had, or at least that is the justification or the reasonability for why one should be able to engage in subtraction on both sides column-wise. But you just have to be very careful when you're doing this, because your associative law under subtraction is not guaranteed. And so be very, very careful when you are using these shortcuts to perform rearrangement. Okay, that being said, let's now talk about perpendicular lines. So the symbol for perpendicularity is going to be this upside down T, and it means that the two lines are essentially crossing perpendicular. They're going to be crossing each other at a 90-degree angle. So here's my y-axis, here's my x-axis. If you have an equation of the line, let's call this one y1, and you have a second equation of the line that is perfectly perpendicular to the first, here's my second equation, they will cross each other at exactly a 90-degree angle. Another way for one to express the idea of perpendicularity is for one to say the word orthogonal. Our textbook doesn't really use the word orthogonal, but if you go to another math class somewhere else, you might encounter this word floating around in the ether, and it actually is synonymous, meaning it's the same thing as saying perpendicular. When it comes to two perpendicular lines, one of the interesting properties that emerges is if you were to represent, say, your first equation of line is y1 is equal to m1x plus b1, and you represent your second equation as m2x plus b2, something special happens. There is, in fact, a special relationship between your m2 and your m1. If y1 is perpendicular to y2, then the following is true. It means that your second slope must be the multiplicative inverse, the multiplicative negative inverse of the first slope. And actually vice versa. So your first slope will be the negative multiplicative inverse of the second slope. Said another way, the second slope is the negative reciprocal of the first slope, and the first slope is the negative reciprocal of the second slope. So suppose you have two equations. One is y is equal to negative 4x plus 3, and the other is y is equal to 4x minus 1, and they ask you the question, is y1 perpendicular to y2? What you have to do is you need to check whether m2 is equal to the negative reciprocal of m1. How do you do this? Well, you first need to write down what you know. In this instance, we know that m1 is equal to negative 4. So all I have to do is plug in negative 4 to where you see m1 in this particular equation. And in this instance, negative negative is a positive. So you'd have a positive 1 over 4. And we check, is this value what you see here? And the answer is no. We see for our m2 that we're given m2 is 4, which does not equal 1 over 4. And the conclusion then is that y1 is not perpendicular to y2. So y1 can only be perpendicular to y2 if you plug in the slope of the first equation into your slope equation, your slope check equation. This m2 is equal to negative 1 over m1. And if it happens to be the case that after you perform the calculation of finding this negative reciprocal, you have a slope that is in fact equal to the slope of the second line, which is what you were originally given, then you have perpendicular lines, but otherwise you do not. Suppose we have another circumstance. We have y is equal to 2x minus 3 and y is equal to negative 1/2 x. plus 1. We can, of course, check to see if if M2 is equal to negative 1 over M1. In this case, our M1 is negative 1/2. Sorry, our negative M1 is 2, rather. So we're going to see, by plugging 2 into this equation, what was our original M2? Well, our original M2 was equal to negative 1/2, which is what we arrived at by plugging M1 into our equation. And so what this means is that we may say y1 is perpendicular to y2 because M2 is equal to negative 1 over M1. And that's pretty much all you have to do. The last section that we'll cover from our particular textbook for this week is what we call graphing linear inequalities. Now, it turned out to be the case that towards the end of our section on linear equations, which was chapter 2, we dealt with a system of what are known as linear inequalities, where you might have x is strictly greater than some value or x is strictly less than some value. And what was interesting about linear inequalities is that you don't get a single solution for x. I saw some students on the exam 1 who are a little bit confused. Well, what do I do now that I've solved for x, right? What does this actually mean? And what it's telling you is when you solve, quote unquote, for a linear inequality, is it tells you the range of values where your original equation is in fact satisfied. So if you had, say, x is greater than 1, you would plot, say, the point 1 somewhere on your graph. You would use a parentheses to indicate that you would never arrive at that single point, and you would shade everything that was greater than that value. And then for x is strictly less than 1, you would have the opposite scenario where you would, say, draw parentheses pointing to the left or pointing towards negative infinity. You would shade everything going towards negative infinity to represent that x could be all values, rather, between negative infinity and 1. So this would look like negative infinity 1. This would look like 1 positive infinity. And we call this our interval notation because it is shorthand for this much more complicated and or involved set builder notation, where you'd say that x is every value greater than 1, such that x is a real number, which was kind of a pain in the butt to write out. So we don't really want to rely too much and or too deeply on that. Well, it turns out that you can also have linear inequalities with 2 or more dimensions. You might have, say, y is equal to y is greater than, strictly greater than 2x plus 1. Suppose we were dealing with a situation such as the following. All you have to do to solve a linear inequality is to simply graph the linear inequality and use some rules of deduction, some basic deduction, in order to determine where a solution exists. And I'm just going to show you exactly how that works. So starting out, you have this equation, y is greater than 2x plus 1. Simply put, just like a regular equation, you could give yourself a number of points, say -1, 0, and 1. And you would, of course, calculate a corresponding value for y. You would find that for -1, 0, 1, 2 times -1 is -2. -2 plus 1 gives you -1. 2 times 0 is 0, plus 1 gives you 1. 2 times 1 is 2, plus 1 gives you 3. So you have this equation of a line where you have a point at -1, negative 1, should be down here somewhere, 0, 1, and 1, positive 3. Okay. Now, if we were drawing a regular equality, and a regular equation, y is equal to 2x plus 1, we would, of course, draw a straight line. But instead, what we're dealing with is we're dealing with a setup, y is strictly greater than 2x plus 1. So the only change that we're going to make here from our original equation is we are going to use a funny looking notation, a dotted line notation, to represent that we can't actually have a point that lies along this particular line. Let me explain. So what we found out was that y has to be strictly greater than, say, the point negative 1. I'm sorry, the point negative 1 if your x value happens to be negative 1. Why is that the case? Well, going back to your original equation, you've got y is strictly greater than 2x plus 1. And if you were to use negative 1 for your y, and you check to see if 2 times negative 1 plus 1 checks out, you're going to get this impossible linear inequality where you've got negative 1 is strictly greater than itself, which doesn't make any sense. This is nonsensical. 1 cannot be bigger than itself. Negative 1 cannot be bigger than negative 1. That is completely ridiculous. And so because every single point that lies along the line represented by y is equal to 2x plus 1 is not a value that actually is satisfied by this particular graph, we are going to instead use a dotted line to represent this particular scenario. Now, another nuance of solving linear inequalities, because we haven't actually solved the inequality yet, is that we are going to shade on our graph every single point where the equation itself would in fact be legitimate. And so let's look at what that kind of looks like. Now, you'll note that at this point, negative 1, you can't actually have any value that lies along this line, right? But I could have a value that lies at negative 1, negative 1, 0. And I could also have a point at negative 1, 1, and I could have a point at negative 1, positive 2. I could have a point at negative 1, positive 3, so on and so forth. It turns out I could actually have an infinite number of points that were above this particular line because y is strictly greater than 2x plus 1. It's strictly greater than all of the points that lie along the line. So said another way, it's equal to every single value that is above the equation of a line. And to just double check this, to see that that's the case, if you were to plug in, say, this value, negative 1, 0, into your equation, your y would be 0, and you can just check, is it the case that 0 is strictly greater than negative 1 plus 1? Well, 2 times negative 1 is negative 2. Negative 2 plus 1 is negative 1. And indeed, you would see that 0 is strictly greater than negative 1. And the same is true for all points that are above, say, this value here, which is at 0, positive 1. Well, we can't actually be along the line at the point 0, 1. We could, in fact, have a y value that is strictly greater than 1. We could have, for example, a point 0, 2. We could have a point 0, 3. We could have a point 0, 5, whatever. And the same is true for this third point. We could have everything that exists above the line as being a value, a point which satisfies our equation. And for this reason, for the fact that everything above the line, or said more specifically, a point that exists strictly above the line, which represents y is strictly greater than 2x plus 1, is a value that satisfies the equation. We shall shade above our line, just like so. Now, I'm not necessarily going to go through the proof for all of these other variants, but it stands to reason that if we apply the same logic as we do here for this y is strictly greater than 2x plus 1 case, it turns out that we can actually create kind of a cheat sheet for all possible linear inequalities. If you have a situation where y is strictly greater than mx plus b and m is positive, you will always have a linear inequality that looks kind of like the following, where you have, say, a y-axis, an x-axis. You're going to have a y-intercept value at 0b somewhere. If b is a value above 0, your line will intersect a y value that's above 0. If b is negative, you're going to have a point that intersects the y-axis that will be below 0, below the x-axis, okay? But, just for the sake of argument, suppose this b happened to be positive. If you have a slope that is positive, your y will the equation of a line, rather, will always be going from the bottom left corner to the top right corner. And because we have a strictly greater than situation, our line will be dotted and we will shade everything that is above. Similarly, if we have y is strictly greater than mx plus b, but m is negative, what's going to happen is you're going to have a point, a y-intercept point, where the line actually passes the y-axis. It will be going from the top left corner down to the bottom right corner. Said another way, the line itself will be traveling from the top left corner to the bottom right corner because it has a negative slope. And everything above your line will be shaded, just like so. And this is, in fact, the solution of this particular problem statement. If you have y is strictly less than mx plus b and your m is positive, then you will have an equation that looks like the following. You're going to have a positive slope for a line that passes somewhere through 0b, and if b is positive, it means it's above 0. Your line will kind of pass through the y-axis like so. And because y is strictly less than all of the values on your line, you will shade everything below this particular line. If you have an equation y is strictly less than mx plus b, but your m is negative, your slope of your line is negative, just like before, we will have a line that is going down into the ground. It is traveling from the top left corner down to the bottom right corner. It's going to pass through our y-axis at some point, 0b. Again, b could be positive, b could be negative. In this example itself makes b appear to be positive. Okay, but just know that if b is negative, your line is going to be down below somewhere. Okay, so just adjust this picture for your particular circumstances. And because your equation is y is strictly less than everything on the line, you are going to shade everything down here. When in doubt, pick points and verify that your equation makes sense. Okay. Now, a somewhat easier thing to graph would be an instance where y is strictly greater, I'm sorry, not strictly, but conditionally greater than or equal to some value. Because what's going to happen is when you have a conditional inequality, whether y is greater than or equal to something, or if it's less than or equal to something, all the points along the line itself are going to be valid. So in this instance, in the instance that m is, say, positive, you have, say, some 0b, some y-intercept somewhere. Your line is going to travel from the bottom left to the top right because your slope is positive. It will pass through the y-intercept value, and your y, because your y is strictly greater than or equal to all, I'm sorry, not strictly, but conditionally greater than or equal to all of the points along the line, you will shade everything above, with the only change from our prior setup being that we will now use a straight line that is not dotted. Okay, it's a straight line that instead of having a dotted line, it will be fully solid. There are no discontinuities. And if y is conditionally greater than or equal to mx plus b, but m is negative, instead of having a line that travels from the bottom left to the top right, it is going to travel from the top left to the bottom right. It will cross through 0b somewhere, and everything above the line will be shaded. For y, whoops, looks like I'm running out of battery, so I'll make this quick. For y is less than or equal to mx plus b, and your m is positive, you will have a equation that looks like so, with everything shaded below, your line passing through the point 0b. And if your equation of a line has m is negative for an equation y is less than or equal to mx plus b, you'll have the exact opposite happening, meaning that your equation of a line will be going from the top left to the bottom right. It'll pass through your y-intercept value somewhere, and you will be shading everything below. All right, so these are the 8 different cases where you might be dealing with a linear inequality, okay? And so that's really all there is to linear inequalities. We're going to get some practice in class, but for now, it looks like my batteries are about to die on my computers and my tablet, so I'm going to leave it to you guys to do some practice on your homework, and then if you have any questions regarding the lesson, just send me an email. I will see you all